Welcome to the afternoon session. So it's a great pleasure to introduce Andy Neitzke from University of Texas. He's going to tell us about topics in n=2 gauge theories.
Am I on? Yeah, okay. So it's a real pleasure to have the opportunity to talk at this school and to visit CERN. I think this is my first time here. So I'm supposed to describe progress in n=2 theories, but more particularly, so in the last few years, there's been kind of a renaissance, or there's been a lot of progress on n=2 theories, and particularly in what I would call exact results in n=2 theory. So exact results in n=2 theories. A four-dimensional gauge theory is a complicated beast. So in a typical four-dimensional gauge theory, you somehow don't expect to be able to compute anything exactly. But for theories with supersymmetry, the situation is better. And recently, it's been understood just how much better it is. In n=2 theories, it turns out to be able to compute quite a lot of things exactly. Things like partition functions on various manifolds, vacuum expectation values of various operators, and so on. And so there's been a big industry in that in the last few years. I want to talk about one sort of aspect of this story, which is not concerned directly with computing partition functions, but rather with computing some aspects of the Hilbert space of the theory. So what I want to focus on is just to describe, one aspect of that progress. Which is new methods for computing not partition functions, but the spectrum of BPS states. And so today I have sort of three hours, so three goals. So first of all, what is a BPS state? And a lot of the progress on BPS states was sort of catalyzed by a rather amazing formula that was written down, actually first it was written down not by physicists but by mathematicians, which is called the Kontsevich-Soibelman wall crossing formula. So my first aim is just to explain what these things are. The second aim, so the Kontsevich-Soibelman wall crossing formula at first is going to look like something completely nuts. It's a formula that tells you sort of as you move around in parameter space of some gauge theory, it tells you how the BPS states can decay and how bound states can form. And the formula, when you first see it, looks like something that you can't possibly understand how it could come from physics. And so the second aim, once we know what the formula is, will be to explain how to actually get the formula. So how to understand or how to prove this KS formula. And the sort of key technical tool in understanding how the KS formula works is going to be to study not just the gauge theory by itself, not just this four-dimensional gauge theory in R4, but to introduce some defects into the theory, supersymmetric line defects. So using these supersymmetric line defects, we'll be able to understand why the wall crossing formula is what it is. And then the third goal will be to actually determine the spectrum of BPS states. So how to determine the BPS spectrum And again, there's going to be a sort of key technical tool. And in this last part, the key technical tool will be not line defects, but surface defects. Supersymmetric surface defects. So to the extent that there's a theme to these lectures, the theme is that you should never just study a field theory by itself. If the field theory has a spectrum of defects in it that preserves some symmetries, you should always, always introduce those defects. Even if you don't think you're interested in them, it will eventually turn out that they help you to study things you are interested in. So all right. So that's the sort of plan. So most of the story that I tell. Well, not most of the story. This has been worked on by a lot of people, but most of the story that I will tell is sort of part of a long-running joint work with Davide Gaiotto and Greg Moore. And I should say that, you know, for studying the spectrum of VPS states in n=2 theories, there's another sort of parallel line of development, sort of parallel approach, which uses quiver quantum mechanics. Quiver quantum mechanics, which was sort of pioneered by Denef and recently has been used sort of to great effect by Chakotay, Vafa, et al. In various combinations. So I feel like I ought to mention this because this is another very powerful way of studying the VPS states in n=2 theories. But I'm not going to. It won't feature in these talks. Okay, great. So let's get started. So we want to study two-dimensional quantum field theories. n=2 supersymmetric quantum field theories in 4 dimensions. And let me first remind you of a few of their sort of basic properties. So one of the key things about these theories is that unlike theories with less amount of supersymmetry, n=2 theories typically they don't just have a single vacuum, but they typically have a continuous moduli space of exact quantum vacua. So it doesn't just have a finite number of vacua or just one, but it has this continuous moduli space. And in general, the moduli space actually has a bunch of different branches which intersect each other just at some special points. So we'll focus on one particular branch of this moduli space, which is the so-called Coulomb branch. So let's have an example right away to see what kind of thing we're thinking about. So let's think about, for example, the sort of prototype example of an n=2 theory, which is just n=2 supersymmetric Yang-Mills with a gauge group SU2. So what are the fields? So the field content of this theory, well, it has the gauge field, A mu. It has a complex scalar field, phi, and then it has a bunch of fermions, all sitting in the adjoint of SU2. And so why am I saying this theory has a moduli space? Well, you go and you write down the action for the theory, and you find, well, it has kinetic terms for all of the fields. And so at least in order to be in a vacuum, the fields are going to have to be constant. Now, what can that constant be? Well, there is a potential. There is a potential for the scalar, but this potential so the potential is of the form trace of the commutator phi with phi daggers squared. And so this potential isn't completely effective at eliminating the modes of the scalar. This potential has some flat directions. So what are the flat directions? So if I take, for example, phi to be of this form, a 0, 0, minus a, well, it's diagonal, so sure enough, if you compute the commutator of phi with phi dagger, you just get 0. So the trace of the square of that matrix is just 0. And so this, and so if you just take the field phi to be constant all over R4 with that particular value, then you get a vacuum. Now, every vacuum, so you might think, okay, well, those are some of the vacua, but probably there's lots more. Actually, all the vacua turn out to be gauge equivalent to this one. So using SU2, using the SU2 symmetry, any vacuum is equivalent to one of these. And moreover, using the SU2 symmetry, you see there's a little bit of redundancy here. Namely, I could use the SU2 to exchange the two diagonal entries. So the vacuum labeled by A here is actually gauge equivalent to the vacuum labeled by minus A. So A equivalent to minus A. But that's the only equivalence. So what we can say is that classically, we have actually a moduli space of vacua. Continuous moduli space, because this A just varies continuously. Parameterized by, not by A, because of this equivalence, A goes to minus A, but parameterized by A squared. Or a sort of more manifestly invariant way of writing it is to say I take the trace of phi squared. And that's actually equal to 2A squared. A squared. So in the infrared, we have this continuous moduli space of vacua. Now, what is the physics in one of those vacua? So suppose I start with the n equals 2 theory with gauge group SU2. I look at the theory in one of these vacua, and I look at the sort of low energy infrared physics. What am I going to see? Well, so if this parameter A is not equal to 0, then what we see at low energies is that the gauge symmetry is Higgsed. Right, evidently, this particular choice of phi is breaking the SU2 gauge symmetry down to just those matrices which commute with that one. That just breaks the SU2 gauge symmetry down to U1. So at low energies, what we find, even though we started with a non-abelian gauge theory, at low energies what we find is a U1 gauge theory. Not SU2. Okay. So everything I told you so far is kind of the classical picture. So the classical picture would be that we have U1 gauge theory everywhere except at A equals 0, and then at A equals 0 we have the non-abelian gauge symmetry restored. The real story is a little bit more, well, so this is not the exact quantum story, but for the moment we're just trying to get a qualitative picture of what the moduli spaces of these theories are like. So I just stick with the classical picture. Okay, so what's the upshot? Okay, so this was just an example. And so, but this is more or less what happens generally. So now for any n equals 2 supersymmetric theory on its Coulomb branch, so the Coulomb branch, which I call B, it's a complex manifold. So here we had just a single complex parameter, this parameter U. In general, we might have a bunch of parameters, but still, they're sweeping out just some complex manifold. And if we sit at a sort of generic point of this complex manifold, the IR physics at a generic point, I'll always use the letter U for just the generic point of the Coulomb branch, is some abelian gauge theory. So what you see in the infrared is just a gauge group, which is, roughly speaking, U1 to some power, U1 to the R. So here was the case R equals 1. Okay. So what we're interested in is we're interested in studying sort of the structure of the Hilbert space of the theory now. But I have to say which Hilbert space, so I have to say the Hilbert space in some particular infrared vacuum. So let's talk a little about what that Hilbert space is going to be like. So first of all, the states of the theory, well, the theory looks like a U1 to the R gauge theory, and so the states are going to carry charges in that U1 to the R. So they carry electromagnetic charges. So electric and magnetic charges. So if you like, one way of saying where these charges live is that we have a charge lattice. I'll call it with the letter gamma, which is just a rank 2R lattice. So for example, in the case we just discussed with rank 1, gamma would just be Z2. So every state can carry some electric charge and some magnetic charge. Now in addition to this, potentially if the theory has some global symmetries, then we might also consider the flavor charges of the states, charges under the global symmetries. But for a moment, let me just neglect these. Somehow the main player in the story I'm going to tell is this electromagnetic charge lattice. So then the Hilbert space of the theory, the Hilbert space now is decomposed into components for every charge. And moreover, if you look at the space of one-particle states, so we're going to be particularly interested in the one-particle states in the theory. And so the space of one-particle states is also decomposed like that. So we have particles with all possible charges. Okay. Well, sorry, maybe we don't have particles with all possible charges, actually. But at least every particle has some charge. Some of those components might be empty. Okay. So now inside of here, we're interested in studying the states of this quantum field theory, but not all the states. I mean, okay, we would love to study all the states. We would love to understand the complete, spectrum of the Hamiltonian, to understand the masses of every single state in the theory. That seems to be a totally intractable question at the moment. If you can solve that problem for ordinary Yang-Mills, you get $1 million from the Clay Foundation. So we have to be a little bit less ambitious and study things particularly that are somehow protected by the supersymmetry. So let's talk a little bit about the representations of supersymmetry. So first of all, what is the supersymmetry algebra here? So, well, the super Poincare algebra. So we have the SO31 Poincare symmetry plus the fermionic part, the odd part, plus actually one extra generator, which we come to in a second, just generates an abelian factor, so I write it like that. Okay, so what is the odd part? So the odd part is generated by the supersymmetry operators, so QA alpha. So alpha is a spinor index that runs from 1 to 2. And so for n equals 1 supersymmetry, I would have just had Q alpha. But here we're n equals 2 supersymmetry, so I have two different Qs, Q1 and Q2. So what's the supersymmetry algebra? I write it like this, sort of suppressing the spinor indices. I would write it like this. The commutator between Q's and their adjoints Q bar gives you the momentum operator. And the commutator, so again, in n equals 1, this is all we would see. But in n equals 2, there's one extra thing, which is if you take the commutator between Q's corresponding to different supersymmetries, so if I take the commutator between the Q1 coming from the first supersymmetry and a Q2 from the second supersymmetry, there's this possibility of an extra generator on the right-hand side, which is called the central charge. And so this Z, so here that P is the momentum, it's a vector, but Z is just a scalar. So if you like, I'll write this out. For a moment, I'll write it out with the indices just to make clear. Well, in fact, I should even write P mu, gamma mu, alpha dot. And then this other one, QA alpha, QB beta, is just epsilon AB, epsilon alpha beta Z. Okay, great. So, so there's the supersymmetry algebra. Now, what is this? So this guy Z is going to be the thing that plays sort of the key role in the story of BPS states. So it's called the central charge. And how does it act? So how does that operator act on the Hilbert space? It acts in a pretty simple way. It just acts by a scalar. So a complex number, Z gamma, on each component H gamma. And moreover, it's kind of linear in the charge. So Z gamma plus Z gamma prime is Z gamma plus gamma prime. Yeah, central charge is upsetting. Okay, so this is kind of the abstract structure of the supersymmetry algebra that's acting on our Hilbert space. And now we want to ask, what do the representations of this supersymmetry algebra look like? So what is, in short, the structure of the Hilbert space? You can. Oh, did I screw up? Here? The bottom one is, well, yeah. That's why I wrote the right side. So when you see how the spinor indices are getting contracted, you see, yeah, yeah. So sorry, yeah. The notation on the left is a little bit condensed, but it's where I don't show you the maps between the spinor spaces. But I think I wrote it correct. Hopefully I wrote it correct. Okay. So let's study now the representations of this algebra. So we're going to do kind of the super version of Wigner's classification of representations of just Poincare. We want to do kind of the super Wigner classification for super Poincare. So let's study representations. And so as usual, just like in Wigner's trick, what you do to study the representations is you say, well, let's economize and just look at particles that are at rest in some particular frame. So let's consider, and let's only look at massive particles, because ultimately our interest is going to be in the massive particles. So let's look at, in short, in massive one-particle states at rest. So their momentum, in other words, is going to be M0, 0, 0. So this is going to define a Hilbert space H1 rest inside of H1, which is inside the whole Hilbert space. So when I'm studying these massive one-particle states, the space of those states is invariant not anymore under the whole Poincare, but just under, so this H1 rest is invariant under just the SO3 little group, right? It's just the rotations. It's literally now, if you think of having this particle sitting at rest someplace, it's literally the rotations of space around that particle. The boosts would change the momentum, so they're now broken. And so from now on, I'm not going to think about the full SO3, 1 spinor properties of these things, but I'm just going to think about their SO3 spinor transformations. And then there's a kind of cool trick for understanding what the representations are going to be like. Namely, it's the following. So let me fix a phase, any phase I like. So just an angle theta. So it's a r mod 2 pi z. And I define these sort of cleverly defined combinations of the supercharges. So I'll call them r theta and t theta. So nothing fancy. I just take the supersymmetries and I combine them in a sort of funny way. Minus e to the I theta over 2 q2 bar. And t theta will be almost the same thing. q1 plus e to the I theta over 2 q2 bar. So now, I've suppressed all the spinor indices, so everything here is a spinor. And in fact, q and q bar would have been in different spinors for the full Lorentz group, but now that I've restricted just to SO3, those spinor representations just become the same. So I can just add them like this and make another spinor. So okay, so I just picked these particular combinations of the supersymmetry generators. Why did I do it? Well, it's because I get the following now kind of cool formulas. So let's look at the bracket of, this is just a new basis actually for the supersymmetry. So I could write the whole algebra just in terms of this basis. And if you do that, just using the brackets that I wrote above, here's what you get for the commutation relations or the anti-commutation relations in this new basis. So again, this is just the supersymmetry algebra acting on the states at rest. So that M there is the mass of the particular states that I'm looking at. So here's what you find. And so in particular, suppose I choose this phase now to be minus the argument of z. So then what's going to happen? So I choose it exactly so that e to the I theta times z is just real. So in that case, these commutation relations become really simple. They just become the bracket of r with r bar is m minus, now that e to the I theta z is real, so this becomes m minus the absolute value of z. T with t bar is m plus the absolute value of z. And all the other commutators are just 0. So the supersymmetry algebra, in other words, boils down to just these very simple commutation relations. Where again, I'm hiding the spinor indices, but the spinor indices don't play a big role. So all of their brackets vanish. And so what have we got here? We've got just sort of two, if you like, two Clifford algebras. Two Clifford algebras, one generated by the R's and one generated by the T's. Each one, if you ask, so these are just really creation and annihilation operators. If you ask what's the representation of those creation and annihilation operators, each one of them would generate 4 states. And if you work out the sort of SO3 content of that representation, it's just 2 singlets and 1 spin a half. Okay. All right, so far it seems like a reasonably sort of technical business. Now we come to the first sort of, the first point that you might remember, which is the following. So we have this formula that the anti-commutator of R with R bar is M minus the absolute value of Z. So now suppose I take any state, say psi, and compute the matrix element of this commutator R with R bar. Well, on the one hand, just by writing this as the commutator, as the anti-commutator, you see right away that this is the norm of the state R psi plus the norm of the state R bar psi. So in particular, it's something that, assuming that we're studying a unitary representation of supersymmetry, this is something that has to be positive, or at least not negative. Now, on the other hand, we just wrote that anti-commutator just gives us m minus absolute value of z. So what do we get? So on the one hand, because this is a sum of positive things, not negative things, it's at least not negative. On the other hand, it's m minus z times something positive. And so what we get is a kind of positivity. Well, it's even stronger than positivity. So it says that in the supersymmetric theory, all of the massive states have a state that's at least equal to their central charge, at least equal to the absolute value of their central charge. So very unlike a non-supersymmetric theory where a priori there's no bound at all. Here there's a bound. The energy is positive. It is not only positive, but it's bigger than or equal to this this central charge. And moreover, there's something special that happens, you see, if this bound just happens to be exactly saturated. So suppose that it happens that this bound is saturated. Well, then this whole thing is zero. So in particular, the state would have to be annihilated by both of these generators R and R bar. So what have we got? What we've got is that the states in this theory sort of come in two different types. So the states at rest come in two different types. So now we think of taking this space of all particles at rest and just decomposing it under the supersymmetry algebra. What are we going to find? Well, there's some states where the mass is bigger than z. There's some states where the mass is just equal to z. The ones where the mass is bigger than z, these are what's sometimes called long representations. And so here, these are representations where both the R's and the T generators act non-trivially. So each one of them generates its little Clifford creation and annihilation operators, creates its little representation. And so these are of the form, if I just write their SO3 content, I'll have two copies of this little representation, 2, 0 plus a half. So this is from T. This is from the action of T. This is from the action of R. And then moreover, those states can act on a vacuum which itself can have some SO3 transformation properties. So if you ask for what are the irreducible representations of supersymmetry, here they are. You start with some irreducible representation of SO3, some fixed spin, and then you tensor it with these things that come from the supersymmetry. So let me call this LJ. And on the other hand, when the mass is just equal to the central charge, then we see a little different structure. We get what's called a short representation, where these R generators just act as zero. They all annihilate all the states. And so they don't generate this little Clifford vacuum. Sorry, they don't generate this little Clifford algebra representation. And so we get representations that look like this. So now, if you like, you can mostly forget how you can mostly forget everything I said up to this point, and just remember that in n equals 2 supersymmetry, you have two kinds of representations, two different kinds of states. You have the ones that saturate this bound and come in small representations, and the ones that don't saturate this bound and come in long representations. Now, so our aim. So the states that exactly saturate this bound, the ones with m equals absolute value of z, are called the BPS states. And so their states, they're kind of as close as you can get they're as close as you can get to have to being, so to speak, ground states. They have the minimum energy consistent with their charge. And so now, since as we said, determining the whole spectrum of states is hopeless, but we could ask, can we determine at least the spectrum of BPS states? Well, okay, so why might you think that you have a chance of computing the spectrum of BPS states? Well, it's because the spectrum of BPS states has a kind of invariance under deformations of the theory. So in short, one possible strategy for studying BPS states is to go to some sort of classical limit of the theory, some limit of parameters where you can calculate everything just using the actual Lagrangian. There, study the states semi-classically. And then deform parameters off to some other region of parameters where you're actually interested in. So in order to carry out that strategy, what do we have to understand? We have to understand, how does the space of BPS states depend on parameters? So this question for a moment is too hard, but it leads to the easier question. How does the space of BPS states, these BPS states make sort of sub-Hilbert space, let me call it HBPS. How does HBPS depend on the parameters? Of the theory. And by that I mean, so we could study, a priori, two different kinds of parameters. We could study how it depends on the coupling constants, sort of UV parameters of the theory, and we could also study how it depends on the choice of a particular infrared vacuum. In other words, a point of the moduli space. So as we move around in parameter space, how does this HBPS vary? So a priori, there's two different mechanisms by which HBPS could change. So let's imagine that we somehow know the spectrum of BPS states at one point in parameter space, and we're trying to study the BPS states at sort of nearby points in parameter space. So one possibility, one thing that you can imagine happening is that, well, some BPS states could just be lifted. So what does that mean? So that means they could just, a BPS state, after all, is just a state whose mass happens to be equal to the absolute value of the central charge. You can imagine that that happens because of some accidental cancellation, and as soon as you change parameters slightly, that cancellation goes away, and the mass of the state becomes bigger than the absolute value of z. Well, all right, that could happen. That could certainly happen, but it can only happen in a way that's consistent with the SO3 symmetry. So for example, let me draw a little example of what could happen. So here I'm going to draw the spectrum of masses. So as we said, the mass, I'll fix now a particular electromagnetic charge. So we're looking at all the states with the same electromagnetic charge. So their mass is bounded below by this absolute value of z. And we might have, for example, a bunch of these long representations, which we're not interested in so much. And then we might have some of these short ones. Let's say we could have 3 copies of this short representation S0, and one copy of this short representation S1/2. And what can happen? So these are some long representations, say L1, L0, L3 or something. So what can happen? Well, as I change the parameters a little bit, so these red ones may move a little bit. You know, their mass depends continuously on every little detail of the theory, so they move in some generic way. And then what could happen is 3 of these little short ones. So take this S0, and this S1/2. Individually, it's impossible for them to move up. Why is it impossible for them to move up? Just because this S0, for example, is too small. In order for them to move up, they would have to be occurring in long representations. And the long representations are all strictly bigger than that representation S0. But what can happen, of course, is that a few of these guys would combine together and pair up into a single long representation. So you can have, for example, this. So if you look back at what I wrote for the representation content of these representations, the direct sum of those 3 short ones is equal to, as an SO3 representation, is equal to that long one. So you can have these BPS states, these little BPS representations can combine together and become non-BPS and move off. So that's the first kind of problem that we've got to deal with if we want to study BPS states is, you know, they can combine together into long representations and move off. All right, so there's a trick for dealing with this. So this shows you right away, though, that, you know, you have at least a potential difficulty with counting, for example, the number of copies of S0. The number of copies of S0 looks like it might be a bad invariant, because here, for example, it just jumped from 3 to 1 when I changed parameters a little bit. So to sidestep this problem, we might define something a little fancier, what I'll call helicity supertrace. Well, I'm not the first one. I don't know who first called it helicity supertrace. But just the following thing. So what I do is I look. So in my Hilbert space of one particle states at rest, I don't just compute the dimension, I don't just compute the number of copies of some representation, but I compute this particular combination, J3 squared, the trace of J3 squared minus 1 to the 2J3. And then conventionally, I put minus a half here. So this helicity supertrace has the cool property that, I think I read it right. So this helicity supertrace has the cool property that it receives just 0 contribution from each LJ. So just evaluate this trace in one of those in one of the long representations LJ, and you just get 0. Which means that this particular thing is not sensitive to those particular combinations of short representations which can join up and make a long one. So what this does is it counts each representation Sj, but with a particular weight. The weight is just minus 1 to the 2j times 2j plus 1. So for example, whoops. For example, so it counts the representation S0 with weight plus 1, the representation S1/2 with weight minus 2, and so on. So this is sometimes called, this representation is sometimes called the massive hypermultiplet. This is called the massive vector multiplet, and so on. So you see it exactly avoids this problem. So the contribution from S0 is plus 1. We have 2 plus 1s and 1 minus 2, so those cancel each other. And so we're left over with just an index of plus 1, and that's the same on both the left and the right. So if, rather than counting the individual representations, if I count this index, I get something that looks like it could possibly be a kind of deformation invariant quantity. So that's somehow the magic of supersymmetry. It lets you define these things that are kind of a priori going to be invariant. You should think of this as some kind of analog of like the Witten index that counts the vacua of a quantum field theory. This is some analogous index which is trying to count the number of BPS states. OK, that's great. And so But unfortunately, there's also a second problem. So not only can states sort of move off from BPS to non-BPS, but it may also happen that as you vary the parameters, a particle which had been just absolutely stable can actually decay. And so you can ask, when does it happen that a particle can decay? So to get some idea when this happens, let's consider sort of the simplest possible situation of just a two-particle decay. So we've got some particle carrying charge gamma that's going to decay into two other particles of charges gamma 1 and gamma 2. So gamma 1, the electromagnetic charge is conserved, so these two have to add up to the original gamma. And let's just ask, what are the sort of kinematic constraints on this decay? So first of all, we start out with a BPS state. So the mass of the original state is equal to just the absolute value of Z gamma. So now, if it's going to decay, if this particle is going to decay, then its mass has to be, of course, greater than or equal to the sum of the masses of the two constituents that it decays into. And those two constituents are also states of the theory, so they also have to obey this BPS bound. So those masses, whatever they are, they're greater than or equal to the z's for each particle individually. Now, on the other hand, those z's, this z function is just additive, so the absolute value of z gamma, well, z gamma is just equal to z gamma 1 plus z gamma 2. So what have we got? So we've got the absolute value of the sum of these two numbers is greater than or equal to the sum of their absolute values. But you remember by the triangle inequality, the triangle inequality says just for any two numbers whatsoever, it's exactly the opposite. So z gamma 1 plus z gamma 2 is always less than or equal to that sum. So the only way that this can possibly happen, is if all of these inequalities are actually equalities. So all these greater than or equal to's must actually be equalities. So what do we have? So first of all, mass 1 has to be equal to absolute value of z gamma 1. Mass 2 has to be equal to absolute value of z gamma 2. And then finally, this triangle inequality has to be equality. So absolute value of z gamma 1 plus z gamma 2 has to be equal to the sum of the individual absolute values. So what does this say? It says, first of all, that the only way that a BPS particle can decay is if it decays into BPS constituents. So these two, the two individual particles have to also saturate this inequality. So the first thing is that the constituents are also BPS. That's the first thing. But not only they're BPS, but they have to have this very particular property that their central charges, so a priori their central charges are some arbitrary complex numbers, but those complex numbers have to actually have the same phase. That's what it takes for this triangle inequality to be actually an equality. So if you like, the phase of z gamma 1 has to equal the phase of z gamma 2. Or another way of saying the same thing is to say that the decay products, they're not only BPS, but they're actually mutually BPS, meaning that. So before I showed you that this property of being BPS, what it meant to be BPS was exactly that it was the states were annihilated by some particular supercharges. And which supercharges they were just depended on this parameter theta, which was the phase of the central charge. So if I have two particles which have the same phase of their central charge, then they're not only BPS, but they're simultaneously BPS. They both preserve the same half of supersymmetry. Okay, great. So and there's a similar, as you can sort of readily imagine, there's a similar constraint for multi-particle decays. So all the constituents have to be BPS, and they all have to have the same phase. They all have to be mutually BPS. And so finally, so what we arrive at is the following thing. So we define this index, which is like a signed count of BPS states. And what we've decided is that it's first of all a well-defined number, and second of all, it's deformation invariant. Meaning that as you change the parameters of the theory, either the UV or the IR parameters, it doesn't change, except that places in parameter space, the only time that that your particle can possibly decay is at a place where gamma is gamma 1 plus gamma 2, and the argument of z gamma 1 equals the argument of z gamma 2. And so if you like, we could draw a sort of picture of the parameter space. We draw a picture of the parameter space. Draw it like it's one-dimensional. Now, these quantities z gamma are some functions of the parameter space. They move as we move around in moduli. And what happens is that it sometimes accidentally happens that two of them have the same phase. And at the moment when they have the same phase, then so I'm coloring in the place where two z's have the same phase. That's a kind of codimension 1 condition, right? It requires one sort of accident. And so it gives me a real codimension 1 locus in the parameter space. So the parameter space is cut by these walls where two z's are becoming aligned. And these are what's called the walls of marginal stability. They're called walls of marginal stability because, as we just saw, even when the particle does decay, it decays sort of exactly, it's sort of only marginally bound. It decays exactly at threshold. The two particles don't come out with any kinetic energy. But nevertheless, it can happen that they decay. And so the picture is, you know, if I start, for example, here, at this point in parameter space, imagine that at that point in parameter space, I know everything about the spectrum of BPS particles. And now I try to learn what's the spectrum of BPS particles at some other place. Well, I can take my information safely to here. But the moment I reach this wall, I have to address the question of which particles are going to decay, how are they going to decay, or conversely, are more bound states going to be formed? And so that's the sort of fundamental problem. Well, that's a fundamental problem in this area, is the problem of what they call wall crossing. So how to determine the spectrum on one side of the wall if you know the spectrum on the other side of the wall. OK. So that's the question we're going to address, but let me first show you one example of a BPS spectrum, just to get things a little more concretely fixed in our mind. So let's go back to the example that I described at the beginning, n equals 2 super Young mills with gauge group SU2. So again, here we said that the parameter space, so I told you classically that the parameter space was just the complex plane. And in fact, even once we include all the quantum mechanical effects, it's still true that it's the complex plane. And it's coordinatized by, before I just wrote classically u is the trace of phi squared. Now I'll write u is the vacuum expectation value of phi squared. That turns out to be still a good coordinate on this moduli space. And let's introduce also the QCD scale. And now, so Seiberg and Witten sort of very famously completely understood the infrared physics of this theory. And the main thing that, in some sense, the main mathematical ingredient in their solution is just to determine what these central charges z are as a function of parameters. So let's expand. Let's take our So if we consider a general charge in this theory, we could expand it as, so we could consider the particle to have electric charge, say Q, and magnetic charge P. So we have these two basis vectors for the lattice of charges, call them gamma E, just the unit electric charge, and gamma M, the unit magnetic charge. And then what Seiberg and Witten found, their sort of miraculous formula. So they gave it, of course, in terms of some geometry of elliptic curves and so on, but ultimately it's a formula which you can just write down. I write it for you just so you see that it's something absolutely concrete. These are some hypergeometric functions. So here are if you want to know the central charge of any particular state, according to Seiberg and Witten, what you have to do is you just have to evaluate this hypergeometric function. So this is where, what the heck is alpha? So alpha is this parameter u, just rescaled by power of the QCD scale. So this is sort of Seiberg and Witten's miracle. One of Seiberg and Witten's miracles. And so now, so what's the picture of this? So what's the picture of the moduli space? So the moduli space, again, is parameterized by this parameter u. And here's what it looks like. So it has two sort of special singular points. One at u equals lambda squared, and that's where one of these z's goes to 0. And a second singular point at minus lambda squared, where another one of these z's goes to 0. And now, so we want to study the spectrum of BPS states in this theory. So as we just said, one of the real important things is to know where is it that the BPS states can decay. So they can decay whenever two of these z functions become linearly dependent. Well, in this case, it's particularly simple. There's only a rank 2 lattice of these z's. So to ask for two guys to become linearly dependent, there's only one way that can happen. The only way it can happen is if the z gamma E and z gamma magnetic have the same phase. Well, that's not an easy question. You have some hypergeometric function, and you have two hypergeometric functions, and you want to know where's the locus of values where those two things have the same phase. But nevertheless, you can work out what the picture is, and the picture is just like this. So this is the sort of wall of marginal stability. It's the locus where this z gamma electric over z gamma magnetic becomes real. And so the spectrum of BPS states now divides into, there's sort of two answers, depending on whether you're inside or outside that wall. So the answer that's been found is that when you're outside the wall, so at large value of this modulus, the spectrum looks like this. So you have one BPS particle, which is just the W boson. And those come in a massive vector multiplet, and so they contribute to this index -2. I wrote -2 for the back a few pages. If you look at the vector multiplet representations, it contributed -2. And then in addition to that, there's this enormous collection of dions. So there's the magnetic monopole, but then in addition to the magnetic monopole with magnetic charge plus or minus 1, you can also give it any amount of electric charge. So these are the monopoles and dions. Let's see. So that's the spectrum outside the wall. And inside the wall, so this you can imagine computing by sort of semi-classical methods, because it's ultimately the region at very large U is also the region of weak coupling for this theory. At small values of U, on the other hand, the spectrum is much, much simpler, actually. So here you have So here you just have one monopole, one dion, and nothing else. So all other omega of gamma equals 0. And here too, at large U, I should have said, all other omega of gamma equals 0. Okay. So in brief, the picture is like this. Outside the wall, you have this relatively large spectrum of, outside the wall, you have this, this big spectrum that you can compute by, in principle, semi-classical methods, because that's a kind of weak coupling region for this theory. You have infinitely many states. You have W bosons and monopoles and dions. When you go now from strong coupling into the, when you go from the weak coupling region into this region in the middle, which is the strong coupling region, what you find is you hit this wall, and virtually all of those states actually decay. And you're left inside the wall, in the strong coupling region, you actually have an incredibly simple spectrum which has only 4 BPS particles. And so all the other particles, if you like, doing this process in reverse, going from inside the wall to outside the wall, almost all of the sort of intricate semi-classical spectrum is built up just by taking down states of a few sort of simple elementary particles. So this spectrum, for this particular theory, this spectrum had been determined by sort of clever consistency arguments by Bilal and Ferrara. So now it's natural to ask, is there sort of a general recipe, you know? Is there a way of just starting with the spectrum on one side, knowing nothing else, and determining the spectrum on the other side? It turns out that there is, and that's this Kontsevich-Teubelman wall-crossing formula, and that's the thing that I'll tell you about next. Okay, go ahead.
Listen, Andy.